All right. Okay, cool. So we left off last time talking about capacitors. I mean, there was a complaint I heard the other day where it's like, I was trying to watch your video, but people kept talking. It was so hard to hear. I got a lapel mic because you guys would talk and the camera would pick it up. But the lapel mic got tricky, so I might start using it again if I could figure out how to recharge it or remind myself to recharge it. But until that happens, don't talk unless you have a question. Okay. So anyway, so we left off yesterday talking about capacitors, and we remember, or we found in the simulation, that Q equals CV, the amount of charge you can put in a capacitor, is a function of its capacitance and its potential. And the capacitance of a capacitor is a function of its area, its dielectric constant, and then inversely proportional to its thickness. So in other words, the thicker your dielectric, the worse off is your capacitor. And the thinner your dielectric, the better your capacitor. And somewhere around here there's a button. There's a little, hey, let's do the simulation, do the presentational one, but apparently it's gone away. So we'll do it old fashioned for you guys. Usually it sits right here. Or maybe I'm going to walk around. Anyway. Any questions about capacitors before we move on? Oh, okay. Hey, this is kind of cool. Electrons take a long time to go from atom to atom to atom to atom. There it is. Electrons take a long time to go from atom to atom to atom to atom. But we know that when I throw this switch, how long does it take for the electrons who are piled up behind the switch to make it into the lights? Everybody count. Okay, so you got a bunch of electrons piled up in here, and I'm going to throw the switch. That's going to open the gate. The electrons are going to go up the wall, across the ceiling, into the lights. Everybody, ready, set, go. How fast?
Pretty fast.
That one was extra slow. Okay, so that one like no time at all. Like, yeah, that took forever to turn on. But we know that when we throw a switch, the lights turn on immediately. But in reality, electrons have to go from atom to atom to atom to atom, which takes time. It's really slow. So why is it that when I turn the light on, the lights on? When I throw the switch, the lights turn on immediately? Why is that? I'm sorry? The electrons are actually moving pretty slow, yeah.
Because they've already made that reaction. Like all you have to do is open the pathway towards it.
It's kind of like this. Imagine you had a hose. And you have a hose, you hook up, you go to Home Depot, you buy a brand new hose, and you attach it to the spigot, and then you have your neighbor hold the hose like this. And you're like, okay, I'm turning on the water. And you turn on the water. How long until your neighbor is wet? Yeah, a few seconds, right? But then, when you turn the water off, and you hold the hose, bring the hose to your another neighbor, and your neighbor's like, boom, you turn the water on, how long till your other neighbor gets wet?
Like 2.
Yeah, a lot less time, right? Because what's already in the hose? It's already in the hose. So why do lights turn on immediately when you throw the switch? Because there's already electrons in all the atoms. You add an electron over there at the switch, and one electron comes out, pops out over there at the light. Okay? There's already electrons in there. And that difference between the difference in a change in electric field and the difference in the electrons is the difference between current velocity and drift velocity. So the electric field, which is the source of the potential, that changes pretty much instantaneously. But the electrons that are traveling from atom to atom actually move a lot slower. That's called drift velocity. It's something like 10 centimeters per second. Yeah, it's ridiculous. As in like, click, and the lights will come on. So drift velocity is actually pretty slow because the electrons have to go from atom to atom to atom to atom. But the change in the electric field, which creates the potential, is pretty much instantaneous. So there you go. Current velocity, instantaneous. Drift velocity, much slower. You ever have to calculate it? No, not until like your junior year in college. You don't have to worry about calculating it. It's a function of density of the materials and electronegativity or the electronegativity of the materials. We don't care about that. You just need to know that it exists. You writing everything you see, or are you summarizing? Good, summarizing. Current velocity, very fast. Current velocity, very slow. Done. All right. Questions before you move on? All right. This next slide got some pretty important math. Okay, so before we get to it, we talked about electrons and protons, or basically charged particles, how they create fields. Just like a planet would create a gravitational field, a charged particle would create an electric field. Remember this? And if you take a charged particle and you drop one into that field, you've got the field, you take a charged particle and you drop it into that field, that charged particle is going to feel a force towards the center of the field or away from it. And because it feels a force and can move, there is a potential energy towards the center of the field or away from it. Make sense? Okay. Now the same thing exists with current electricity, but instead of one charged particle moving towards a low potential from a high potential, you have a whole bunch of charged particles moving from a high potential to a low potential. Just like water coming out of a hose. Water, if you have like a bucket of water, you have high potential, splash, low potential. Or you have a hose, high potential, low potential, constantly high, constantly low. So charged particles have potential energy, but moving particles also have potential energy. So we talked about what the volt is. Volt is the potential. If you're curious about winning at Jeopardy, the volt is named after Alessandro Volta. Kind of cool. Current is the flow of charge, named after Andre Ampere. It is 1 coulomb per second. We talked about this very briefly in the simulation, the very last question in the simulation. Current is an ampere, and an ampere is 1 coulomb traveling through 1 second. So the last question in the simulation said, how much charge do you have discharging from the capacitor? It discharges over a certain amount of time, that gives you current. You have this amount of charge discharging to 0 over a certain amount of time, that tells you the average current that the capacitor discharges. Okay. Now, when you have current traveling through a potential, you have power. Power is named after James Watt. All right. Remember when we talked about the electron volt? Do you remember what the electron volt is a unit of? An electron volt, an eV, is a unit of energy. It's a unit of energy. It's similar to the joule. In fact, 1 eV is equal to 1.6 times 10 to the negative 19 joules. Do you remember the formula? If you flip back a couple pages, do you remember the formula for potential energy of a charged particle? Yes.
Change in U equals change in V cubed.
Change in V cubed. No, I'm not even going to put the changes in there. We can put the little deltas in here. I'll make them tiny. Tiny U, tiny V. Okay, U equals V cubed. Okay? So in other words, a charged particle will have its energy changed when its charge is moved through a potential. Make sense so far? So a joule is equal to a volt times a coulomb. So far so good? Now, let's divide that by time. So let's divide joule by time, and let's divide volt coulomb by time. So a charged particle, at the moment it starts moving, it's going to have an amount of energy equal to volt times charge. But if charges are moving over time, then you get this situation. What is a joule divided by a second? Or this should be seconds, this is the time. So seconds, seconds, this should be time. What is a joule divided by a second? Nope. Joule is a unit of energy. Second is a unit of time. Energy divided by time is power. Yeah. So a joule divided by second is a watt, which is power. Volt. What is a coulomb divided by 1 second? It doesn't matter, right? We just learned it. It's an amp, right? It's an amp. This is voltage. This is current. That's an N, current. Power equals voltage times current. Or a watt is a volt times an amp. So, formula for power, what is the formula for power? Current times voltage. And that's why. A watt is a current of 1 ampere traveling through a volt of 1 volt, a potential of 1 volt. You should also write down this one. This is going to make sense in just a little bit. P equals I squared R. But the big one we want to use is P equals IV. Power is current times potential. And that's why. Just to link it to electrostatics. A particle, a single charged particle in a field has a potential equaling its charge multiplied by the potential it travels. A whole bunch of particles traveling over a time have a power equaling the potential multiplied by their current. Equals IV. Am I being clear? I must be, because Audrey's drawing pictures. She's like, I'm so bored. I have to draw. I must sketch. Very bored. Okay. Give me a thumbs up if this makes sense to you.
It makes sense, but I don't know when to apply the.
I totally understand. And you're going to get to a point where you're just going to plug and chug, but to get those dendrites extended into other areas of your brain, it's important to realize how this and this relates to what we previously learned about electrostatics. So that's what I'm trying to do. Like, I is Q over T, great. P equals IV, great. You can just plug and chug. But it helps to know that this is the current electricity power, and it relates to the energy of a charged particle in a field. And we move on. America's falling asleep. Okay, Ohm's law. Ohm's law is V equals IR, as far as you know. You're going to use this a lot. V equals IR, V equals IR, V equals IR, V equals IR, V equals IR. It's not a great, it's a very easy to remember formula. It should be written, the current is potential over resistance, but V equals IR just makes more sense. It's just easier to say. It rolls off the tongue. You can tattoo it on your arm. In fact, we're going to do these things called verb charts. Verb charts that start with verb. Do a verb chart. You're going to love verb charts. It's like, oh, verb charts are fun. If you thought charts were cool in math, wait till you do verb charts. Okay, so what does this mean? Basically, it means this. If you have charged particles traveling through a potential, and they're encountering a resistance, the current or the speed of those charged particles will be a function of how much potential they have. In other words, how big is the cliff, or how strong is the pump, divided by what's getting in the way. So current is the speed of the charged particles. The bigger their cliff, the bigger the cliff the water's falling over, or the bigger the pump, the stronger the pump, the more current you're going to get. But when things get in the way, you're going to get less current. Make sense? Let me show you an example of what happens when current travels and R is basically negligible. Okay. So the resistivity of my screwdriver, metal, has an extremely small resistance. I'm going to take a big charge and I'm going to dump it through the end of this screwdriver. The screwdriver has an itty bitty resistance. How big was that current? Big. Huge. Huge amount of current. As in, like, touch it with your finger, it's going to hurt a lot. It's going to send a lot of coulombs through you very quickly. Okay. So V equals IR. The current you get is a function of how big the potential is and inversely proportional to its resistance. Cool? Then there's this equation. What is this equation? Anyone have an idea?
Resistance equals something over.
Exactly. Its resistance, in this case, the A is a variable, not a unit. So A is area. So this is the resistance of a wire, and the resistance of a wire is a function of its resistivity, basically how good of a metal be it, and its length, and inversely proportional with its area. So the resistance of a wire varies with how good of a metal it is. Seriously, it's called its resistivity, its resistitude, it's a resistance factor, and its length, and inversely proportional with its area. So, using this idea in that equation, what has more resistance? A thick wire or a thin wire? A thin wire. What has more resistance to student flow? A small door or a big door?
Small door.
If you want to get out of the room as fast as possible, do you want to go through a big door or a small door?
Big door.
Big door. Okay. So a small door has more resistance to student flow. Similarly, if you had to get out of the room, are you more likely to get out of the room faster if you just had to go through a door, or if you had to go through a door and then a tunnel? Just the door. The door's gonna be fast. If you have to go through if you're going through the door like, I'm out of here. You have to go through a tunnel. You're like, so wires do the same thing. The longer the wire, the more resistivity or the more resistance you have. The more crappy your metal is, the more resistance you have. But the bigger the area, the less resistance you have. So if you're going on a beach party and you have to use a long extension cord to plug into the house, should you use a thin extension cord or a thick extension cord? Thick. Thick. Because a thick wire, big cross-sectional area, is going to have less resistance. You're basically wasting electricity through resistance. It basically heats up. Have you ever looked at those old bulbs and the tiny little wire inside? Is that tiny little wire thin or thick? It's pretty thin. Yeah, it's pretty thin. So resistance is named after a guy named Georg Ohm. It is the ohm. And the unit for resistance, I guess we just ran out of English. Now we're going to start using Greek letters. And it's the omega. Hey, where's Georg's thing? There he is. Okay, we'll come back to that. So the unit for resistance is the ohm, and it is given the letter omega. Your speakers in your house are usually 4 ohms or 8 ohms, maybe 12 ohms. To make an ohm, you go horizontal, loop, horizontal. That's how you make an ohm. It's a Greek capital omega. Omega is like the Z of the Greek alphabet. It's a capital omega. Not to be confused with lowercase omega, which gets used a whole bunch in chemistry and physics too. They just like omega. Okay, Ohm's law. Now, I told you this is Ohm's law, and I told you that was Ohm's law 10 minutes ago because a lot of people are going to say, using Ohm's law, or Ohm's law is this. This is not Ohm's law. Listen carefully. When someone says this is Ohm's law, they're actually not telling you the whole picture. This is not Ohm's law. This is Ohm's law. Because a law in nature describes how materials work, or how nature works. Just like the law of gravity describes how gravity works, and we come up with Newton's law of gravity based on the formula. Well, this is the formula that Ohm's law gives us. And it simply states that the resistance of a material does not depend upon the size or direction of the voltage applied across it. Because if it does, we have to use calculus. And who wants to use calculus? Differential equations, multivariable calculus, yuck. We only want one variable to change at a time. So it basically means R does not depend upon V. Does that make sense? So I will depend upon V and R, but R doesn't depend upon V. Because if R does depend upon V, then you have a multivariable calculus question, and you don't want to do that until you're like sophomore year in college. Okay, so we say that a material is ohmic. Materials that are ohmic don't change their resistance based on the voltage applied to them. A good example of an ohmic material is your cell phone. When you, for the most part, unless you have a Galaxy Note 3, when you use your cell phone, it doesn't like start heating up and like glowing most of the time. It's your battery might, but the cell phone itself, it doesn't. So the wires in the cell phone, they're pretty much the same as you use them. Your calculator is a good example. Your calculator doesn't heat up and glow when you use it, whether it's on or off. Can you think of a material that is non-ohmic, where the resistance actually changes when voltage is applied to it? Light bulbs are a great example. The filament inside of a light bulb, it glows when voltage is applied to it. So it's very, very non-ohmic. Another non-ohmic device, a toaster. Those little filaments that get red hot, those things are non-ohmic. When you apply voltage to them, their resistance changes radically. Okay? So if a material starts to glow or fall apart, it's non-ohmic. If it doesn't, it's ohmic. Get the idea? Paper is, well, yeah, paper is non-ohmic. If you run enough voltage through paper, it will start destroying itself. Okay, does that make sense? So Ohm's law equals IR comes from Ohm's law. Resistance doesn't depend upon the voltage applied to it. I have to tell you the difference because it's important that you know this stuff. Some physics teachers will be like, Ohm's law is V equals IR, next page. That's not what Ohm's, this is the result of Ohm's law. This is not Ohm's law. Okay. The little, the rho? Yeah, this rho stands for resistivity of the material. So it's basically how good is your metal. Yeah. So gold has an extremely low resistivity. Copper has an extremely low resistivity. That's why you use copper wires in your phone and gold contacts on your safety equipment in your car. Aluminum has really crappy resistivity, a very high resistivity. So when you buy wires, a lot of cheap wires are aluminum because it's cheap, but they suck. You want to see what kind of wire you have? You can cut your wire and like, oh, steel. Ooh, copper, that's a good one. Cut my copper wire, do that. Good wire. Yeah. So insulators have very high resistance, conductors have very low resistance. Okay. This basically summarizes what we were talking about, but adds one more thing. Okay. As wire diameter increases, as A, so A is cross-sectional area, thickness of your wire. As A increases, your resistance decreases. You know, you're writing that down. Yeah. While you're writing that down, I'm going to do something kind of cool. This is actually a lot of fun. scissors.
Save the turtle.
Save the turtles.
Classic Shaw spell turtles.
Oh, right. California. Silly Californians. Now, if you have issues with putting your mouth on these things, I understand you don't have to do it, but it's kind of fun.
Have they been used before?
No.
Oh, okay.
And we're going to throw them away and then choke out the turtles.
No.
Oh my gosh, California is so idiosyncratic because they're like, we have to save the world, no more straws. I'm going to get in my SUV and drive 40 miles to go to a movie. What the turtles? It's like, I can't believe California. They drive so much, do such stupid little things. And they're like, we have to get